my thesis, I took particular interest in the installation of software. Nowadays, when one installs a software, you don't install it yourself, but you use an app store. So whether it's on your phone, Android, Mac, iOS, etc., what you do is you use a software and you ask it, please, I would want to install Firefox. The technologies behind such app stores are very different in the different ecosystems. So we're going to be interested in only one. And we're going to have a look at Debian. Debian, for those who don't know, it's a Linux distribution, which is basically an operating system. So that's like Windows or Mac, but different. And it's very widely used as an operating system for servers, so the machines that run the internet, basically. As an operating system for desktop computers or laptops, so personal computers, and as a basis for derived distributions. And I guess here the most well-known would be Ubuntu, but there are numerous others. In Debian, if you want to install, well, Firefox in this example, one way is to open a terminal and write in the terminal apt install Firefox, which is you as a user asking the apt software, which is an app store, to install Firefox. What you get then is some text, some more text, some more text, and then at some point you're done. And Firefox is on your machine, and you can use it, and it's magical. Except, of course, it's not magical. And the way apt here knows how to install Firefox is through something that we call a package. Let's thus have a look at one package, and in that example, the package for Firefox. Package is a file with the .deb extension, and if you open it, you'll find two parts, two archive, one called control, the other called data. The data archive contains a lot of files. We can see, for instance, user bin Firefox, which is the actual Firefox binary. We can see configuration files and a lot of other files that are necessary for the work of the software. If we have a look at the control archive, we find several sub-files. One of them is called control as well, and it contains metadata on the package. So the name of the software, its version, the kind of computer it can run in, the dependencies, that is the other software that needs to be installed in order to have Firefox working on your machine, etc. And more importantly for this work, we find these post-inst and pre-rm files. And if we open them, we find this. And this is a shell script. That is a tiny program in the shell scripting language. That does mean that at some point, when trying to install Firefox, we'll have to run tiny programs. How so and where? If we come back to our terminal output from before, we have first the user request, so written by the user to request installation of Firefox. We have a phase of resolution of dependencies, when we figure out which software need to be installed in order to have Firefox working on the machine. We have then a phase of downloading of the package, because keeping all the package on one's computer would be impossible. So we just download them on demand here from the internet. And then the actual process of installation starts. We have first this phase called preparing to unpack, which consists in running the script pre-inst for pre-installation. We have then the phase of unpacking, which consists in taking all the files from the data archive and copying them on the system, on the machine directly. We then have a phase of setting up, which consists in running the post-inst script for post-installation. And finally, we have a phase of triggers, and that's just other software that needs to be made aware of this newly installed software. And here we can, for instance, see the menus. And of course, there is a new software, so the menus need to be updated to show this new software. And then we're done. The important part here of interest in this thesis is this. We run shell scripts, the one we saw before, and more importantly, we run them as the root user. The root user is the administration user, and it can do anything on the machine. So that does mean that if something wrong happens in these scripts, and in shell it can be easy, if something wrong happens in these scripts, the consequences can be catastrophic. In this context, what could possibly go wrong? Well, a lot of things, and there are numerous examples of times where things did go wrong. This is one I like in particular. This is a package called CMI-grep, and this person here files a bug report saying that in the version 1.1.3-1, when you install CMI-grep, you break unrelated software. So you're like, I'd love to play with CMI-grep, apt install CMI-grep, then CMI-grep shows on the machine, you play with it, you're happy, and later, 10 minutes, an hour, a day, a decade, you try to use something else and it doesn't work and you have no idea why. That's basically the problem that we try to work with in this thesis. If we read the description of my thesis, the goal is to apply formal methods to shell scripts and to the quality assessment of Debian packages in particular. If we reformulate, that means using already existing formal methods and applying them and potentially updating them in the process in order to make sure that when someone installs, updates, or removes a software, they do not break other software or break the whole computer if you do break a key software, or remove files from the user, etc. It's a tough problem. It's complicated because we manipulate really complex objects. We manipulate shell scripts first, and for those who have played with them, it will not be hard to convince you that the syntax is rather treacherous and the semantics is really unusual and complex. That does mean both that it's easy to make a mistake and therefore this is an important problem, and also that these scripts don't easily play well, like they don't easily play with static analysis or the usual tools. Moreover, we work with Unix file systems. So that's the tree of directories that one has on their machine, where directories store other directories, etc. This is basically trees, but not exactly, because they contain a lot more information and they can actually have links and symbolic links, etc. So they're really complex data structures. And we don't only work on them, but on Unix utilities, which are objects that transform the previous these data structures. So we have complicated programming languages that manipulate a transformation of complex structures, and it's hard. The plan of the goal of the PhD is to be able to take a package with the metadata, the static contents, and the maintainer script, and to produce a report that we can then send to package maintainers being like, well, in this case of the installation, there can be this thing happening, and that's a bug. Now, first thing is that we take the shell scripts and we parse and convert them to an intermediary language that is cleaner. This is because shell is really complicated to work with, so we just decide to convert it. This language is cleaner in the way that its syntax and semantics are clearly defined in a formal way. And it tries to avoid a lot of pitfalls of shell scripts. In this area, my contributions are a contribution to a parser for POSIX shell, which is already quite a bit of work, and the definition of this intermediary language and the conversion that goes with it. Once we have these scripts in this intermediary language, we run a symbolic execution on them in order to compute their semantics. This semantics is expressed in the logic of our own doing, which we call FTS. That's a feature tree logic. They have been studied before, but we had to extend them for our use. On this newly introduced logic, FTS, we work on decision procedures. And we work in two lines. One is more theoretical and leads to decidability results. And the other is more practical because the goal is to write an actual tool. And so we have efficiency considerations for our decision procedures, and then, of course, implementation considerations. Once we have the semantics of all the scripts, we have another layer of symbolic execution, which takes the metadata, the static contents, and the previously computed semantics, and runs scenarios of installation, update, removal, etc., and then produces a report for the package maintainers. In the rest of this talk, I'll really quickly talk to you about symbolic execution, because although it's not technically our contribution, it's really important to understand the semantics and what we need on the logic behind. I am then going to spend most of my time describing the work we've done on these semantics, on this logic, and then I'll quickly show you the kind of reports that we obtained in the end. So let's talk about symbolic execution. Here is an example shell script, which does, if userlib, the path userlib, does not exist, the bang is the negation and test minus e-test the existence of something. So if userlib does not exist, then we create it as a directory. And then if userlib foo does not exist, then we create it as a directory. The goal of symbolic execution is to explore all the possible traces of execution of this script. So we say, whatever happens, the first thing we do is test whether userlib exists. This can either succeed or fail. In shell, all the comments return either 0 or non-zero, 0 being the success and non-zero being all kinds of errors. If this test succeeds, then because of the negation, we skip the whole if and we go straight for the other if. So we do another test. Similarly, if this test succeeds, we end at the end of the script, and that's one possible execution of the script, ending in a successful output. If this second test fails, then we run makedir, and we try to create the path userlib foo. And this can lead to either a success or an error. And there are two more branches. If the first test failed, we would have to try to create userlib, which would either lead to, with success, the same tree as before, because we end up here, or with error, that's already the end of an execution here. What we call a trace of execution is a path in this tree saying first there is an error of this test, and then a success of this makedir, and then an error of this test, and then an error of this makedir. This actually tells us what we need for the logic behind, because what we want to be able to do is for each of these traces to say, this is how things looked before in the tree, in the file system, and this is how things look after. So we want to be able to express tree relations. We need a logic able to do that. We need enough expressivity to specify cases of these utilities, so the test userlib, the makedir userlib, etc. We need to be able to compose such relations, because we need to be able to say, well, I know what the error of test does, I know what the success of makedir does, I want to compute what happens when I do first the error of the first one and then the success of the second one. And then, more importantly, we want to be able to detect impossible cases. As an example here, in this trace, we're in the success case of makedir. So userlib was just created and is therefore empty, which means that the test userlib foo will always fail because foo cannot exist in userlib. So this success here is unreachable. Similarly, this makedir will always succeed because foo does not exist. So this error here is unreachable, and only this success is reachable. Finally, we want to be able to do the whole thing incrementally, because we want to be able to run it at every step. We want to compute test and then be like, if this error is reachable, I continue. If not, there is no need to explore the whole tree. And then if this makedir succeeds, I want, if it is possible that this makedir succeed, I want, and only in that case, to continue exploring the whole tree, etc. So we want to save all the computation that we have previously done and avoid recomputing always from the beginning. This leads us to the definition of FTS, this feature tree logic. Feature trees have been studied in the past. They are basically trees with labels on the edges, and these labels help you select a subtree. So in this whole tree with etc, we can select this subtree, and there is just one that goes by etc. The formal definition we take here is that a feature tree is a partial function from what we call features, that's the legal names, the legal file names, to feature trees. This one, for instance, here is the partial function of domain etc and user, and in etc it goes to this feature tree. All right, we take an inductively defined, we take an inductive definition, and we force the function to have finite domain so that we only consider finite feature trees. These objects have been studied before, but with feature tree logics, and I'm going to present one of them. I'm going to present FTS. In this logic, we have several predicates. The first and most important one would be the feature predicates, saying that from the variable x, we go to the variable y through a feature f. And evaluation row would satisfy this predicate if the tree associated to x has f in its domain, and through f leads to the tree associated to y. Another predicate will be the absence predicate, where the set is either a finite or a cofinite subset of features. And that states that the names from this set are forbidden in the tree of x. So the domain of the tree associated to x must not have anything from f. And we'll have the similarity predicate, which is a binary predicate, stating that the two trees for x and for y must be equal on the set f here. So it's a partial equality of tree. And then we compose these with negation, conjunction, disjunction, existential quantification, but only, and universal quantification, but only on variables, not on features. It's actually well known that if you quantify on features there, you get really easily undecidable. These logics have been studied before. Actually, if you take the feature and the absence, but only of finite sets, you get something called FT in the 90s. And if you take also the cofinite set, you get something that has been called CFT in the 90s. The new contribution is this new similarity predicate that allows to express relations of trees. In this presentation, we're going to use a graphical presentation because it's more practical than to read logical formulas. We'll write the feature as a dash from a variable to another with labeled by the feature. The absence will be an edge from a variable to bottom, or just straightly the absence in case of cofinite set. And the similarity will be a dotted edge between the two variables labeled by the similarity. We can already see that we can express the equality with the similarity of the full set. This is a notation for the full set. Or the update. And here, for instance, we say that the variable x does not have anything in f, and y has something in f and it goes to z, and x and y are similar except in f. This is the notation for the complement. This basically tells you that y is an update of x, where there used to be nothing in f, and now there is z. Except the similarity is much more pleasant to manipulate than such an update predicate, because you can already see that it's symmetrical, it will be an equivalence relation, it will have a lot of good properties. This is already enough to write a specification. If we take make deal user lib foo, we can already write that it succeeds when user lib exists but not foo, which we can write from the initial root user lib exists but not foo. And then it transforms the tree, and the output tree R prime has user lib foo. Foo is empty. This is the absence of everything, so therefore the emptiness. And the output tree is similar to the input tree, except in user lib and foo. We can also write the error cases of such a comment by saying that, well, either user did not exist and nothing changed, or user did exist but not lib and nothing changed, or user lib foo already existed and therefore we could not create it. If we take these two trees, for instance, and we give a valuation that gives the first tree here to R and the second tree here to R prime, this is indeed a valuation that satisfies this formula, because the two trees are the same except here where the first tree does not have foo and the second one has foo. Now, great, we have formulas, we can write specifications. How do we compute with them? We compute with them through a system of rules that will transform conjunctive formulas. So there are rules that will match patterns in conjunctive formulas and transform them by replacing them by something else, possibly under a side condition. An example of rule would be the propagation of the feature through the similarity, saying that if you know that from x through the feature f you can go to z, but you also know that x and y are the same in a set that includes this f, then you can deduce that from y, you can go to z through the same f. Another example is deduction from two features that say that if from the same variable you know that you can both go to y and both go to z through the same f, then you can deduce that y and z are equal. And we have another kind of rules, which would be clash rules that detect inconsistencies. And for instance, if you say that from x, you can go to y with an f, but also this f is forbidden, then of course that's inconsistent, and we can replace the whole thing by a button. This gives us a system of rule, which we call R1. And this system is able to transform conjunctive formulas into sigma-1 formulas. In the previous slides, we would see only conjunctions or false, but it could be other kind of sigma-1 formulas. We can already see here that it's possible then to take these sigma-1 formulas and put them in a form that is a disjunction of an existential quantifier and then a constraint. This we call a DXC for disjunction of existential constraints. And then we'll have tiny constraints here where we can apply more rules and we can reiterate the process as much as we want. So we can use the rules of R1 to write a function which we'll call transform1, able to take any sigma-1 formula and transform it into a DXC. We can write this function such that it terminates on all inputs, and such that if you give it a formula phi, you get a psi in return, and psi is equivalent to the phi. And all the constraints, so all the tiny ci's in the psi, are irreducible with respect to R1. That means no rule can apply anymore. This comes directly from the fact that all the rules of R1 are equivalents. The fact that we reach irreducible constraints comes just from the fact that transform1 is written in a way that it tries to apply rules as much as possible. And the termination is actually really complicated. It relies on a strategy of evaluation of R1. And after pages of definition, we can show that the constraints in the function transform1 decrease for an order in N8, and the definition of the columns is not pleasant. Now, it's good that we can transform and apply rules of R1 as much as possible. It's only useful if we can say something about the constraints to which nothing applies. So what can we say about irreducible constraints? Well, first of all, we can say that they are satisfiable, which will be great for our symbolic engine. Actually, we can say more. We can say that they have the property of garbage collection that we'll read now together. Take a constraint that is irreducible with respect to R1 and take a set of variables that is ancestor closed in this constraint. I'll come back in a second to what is ancestor closed. Then the formula there exists X such that C is equivalent to this, and this is the constraint C to which you remove, from which you remove everything that mentions X. So that's all the literals of C that do not contain variables of X. This theorem allows you to remove a lot of literals from the constraint. The ancestor closeness is that if you take the formula and you see it as a graph, for the feature predicates, you forget about everything else, you consider only the features, you will see a graph. And an ancestor closed set is a set of variables such that if you have a variable, you have all its parents and ancestors. In another way of saying that is that it's a set into which no feature enters. We can already see that if we take the whole set of variables, this gives us the satisfiability because the formula quantified on all these its variable is equivalent to the empty conjunction, which is true. Also, if we take a formula that has some of its variable quantified but not all of them, and we manage to find a subset of the quantified variables that is ancestor closed, this theorem tells you that you can just remove these variables. And this is where it gains its name of garbage collection, because you can remove all the things that are not accessible from free variables. Now, said like this, it sounds trivial, but do remember that we only look at this graph of accessibility through the feature predicates, but we allow ourselves to remove all the predicates and all the literals. This theorem gives us two things. First of all, it gives us an incremental test of satisfiability, because we can just, when we want to check for a trace, we run all our system of rules, and either it gives us an empty disjunction when it's false, or a disjunction from which all the constraints are irreducible. And then we can clean up the constraints by removing a lot of useless stuff. And later we can start again from this newly obtained cleaner formula. So let's see an example here. If we want to have a trace that does make dear user lib in the success case and then make dear user lib foo in the success case, how do we obtain the formula that describes this? Well, we take in our database of specification the specification of the first make dear and the second make dear. These are the formulas we've seen previously. And then we say, well, if we do them twice in a row, that means that the second tree here and the first tree here must be the same. And here we obtain a formula from an input route to an output route. We can start applying rules of R1. Two variables that are equal can be merged together. From the same variable, two features live with the same name, so we can merge them. We can apply that again. Here we say that both from y12 there is nothing, but there is also not foo, so the second is redundant and can be removed. Here we say that R1 is similar to R12, which is similar to R2 prime, so we can compute a similarity already between the two variables. And finally, here we say that 1y2 is empty, but it's also basically the same as 1y2 prime, except in foo, which means that y2 prime can only have foo and nothing else. No rules apply anymore, so we can reach a state of in which we can apply the garbage collection, and this set of variables in the middle happen to be ancestor closed and existentially quantified, so we can simply remove it. And we obtain a formula from the input tree and the output tree, which is rather clean and readable. The fact that we obtained a formula and not false, which would technically be a formula, the fact that we obtained a formula that is not false means that this trace of execution would be satisfiable. If, for instance, we would want to do the success of the first one and this error of the second one, we would take the specification of both, we would identify the variables in the middle, which would start merging these, and merging these, and then detect that at the same time here, we say that y12 must be empty, but it must also have foo going to the 2. And that's non-satisfiable, and therefore this trace of execution is not reachable. So that's one use of the garbage collection as a way to, like for our symbolic engine, basically. We can see how it will work for the symbolic engine. The other use is that it's exactly the right theorem to build a procedure of decidability, to decide the first order theory of the logic. Our logic does not have the quantifier elimination in the strict sense. That means if you take any formula with quantifiers, we're not necessarily able to remove quantifiers. This example formula here, on the free variable x, it means that there is a f going to y, and the y is empty. And we do not know how to express that without quantifiers. But what do we have? We have the garbage collection that removes existential quantifiers. And it's able to remove any non-reachable existential quantifier. And for the others, we are able to switch them to universal. So in the example above, we can re-express it by saying that, well, x must have f, which is the negation of the absence. And then for all y such that x goes to y through f, then y must be empty. And this indeed says the same thing as this formula. We can do that for all the variables that are reachable, and it's great because garbage collection has removed all the others. So in general, we can transform any sigma 1 formula into a pi 1 formula. And this allows us to apply something called the weak quantifier elimination, which will one by one remove all the quantifier alternations from a formula. And in the end, I'll spare you the details, but in the end, we can reach that the first order theory of FTS is decidable. So we can write a procedure that takes any closed formula of FTS and is able to say whether it's valid or invalid. Okay, that was for a theoretical part. Now, what about in practice? What about our solver or symbolic execution? Well, in fact, transform one that we've defined is not really usable in practice. And that's because symbolic execution is a tool that is extremely sensitive to combinatorial explosion. And in this work, we have three sources of these. The first one would be the traces of execution of the script themselves. If you take the example script from before, it was a 6-line script, and we already had 7 traces. And basically, every time you add a new construct or a new command, then you multiply by 2 the number of traces of the script. This is why it's so crucial to be able to remove the unreachable traces of execution. A second source of explosion comes from the rules of R1 themselves. We haven't seen those yet, but you have rules that introduce disjunction and even new variables. So every time you do that, you multiply by 2 the number of constraints you're considering in your disjunction of constraints. And finally, the third source of explosions comes from the specifications themselves. Because if we recall the make dear from before, for instance, we had 1 success case, that's good, but we had 3 error cases. And it would be much better to be able to have just 1, because it would avoid that the symbolic execution explore 3 times, 3 variant of the same thing. So how do we deal with that? Well, for the first problem that R1 introduces disjunctions of new variables, if we look at this formula that says that if you have the negation of a feature, you only replace it by this, we define a new system of rules, R2, that tries to hold on to such literals until it knows exactly which side of the disjunction to choose. As an example for this, we would split this rule in 2 new rules, saying that if we know for sure that we're in the first case of the disjunction, then great. And if we know for sure that we're in the second case of the disjunction, great. But if we don't know, we just keep this literal around, and we'll just make sure in the proofs that we know how to handle it. The result is a system that does not introduce disjunctions or new variables at all. Oops. That's not good. Sorry about that. The result is a system R2 that does not introduce any disjunctions or variables. But in counterpart, we lose this property of garbage collection that we had, and therefore this system is useless to build a decision procedure for the first order theory. But actually, we can still recover partial garbage collection, and this will be good enough for the practical use. All right, so it's not good for the theoretical aspects, but it's great for the practical use. And we can still prove, but the proof gets more complicated, that the irreducible constraints are satisfiable. For the fact that the specifications have a lot of disjunctions, so if we take the example of before, we had like these 3 error cases here. So either user did not exist, or user did exist and led to something that did not have lib, or user lib foo did exist. In order to re-express that in more compact expression, we introduce threaded constraints. And a threaded constraint is the conjunction of a main constraint and threads. And each thread is an implication from a literal to a threaded constraint. And we can then chain threaded constraints. In a way, the threads here are lazy computation that we keep there, but do not necessarily work with. And we'll only actually look into them when we know what to do with them. We'll see what it means in a second. This specification here can be rewritten in 1 threaded constraint only that says that, well, if user exists, then it must lead to some x. And then if this lib and this x has lib, then it must lead to some y, and this y leads to some z. All right, and that's these 3 cases written as 1 threaded constraint. And then we have rules of the form, well, if the main constraint entails one of the literals here, that means we know for sure that this thread will happen. Then we can activate this thread, and that means transforming the threaded constraint by putting the T1 here in the main constraint. All right. On the tool chain that we have written, that runs on hundreds of thousands of scenarios with a timeout of 60 seconds to kill execution if it takes too long. Without this optimization, it used to run in 8 hours, 25 minutes. And it used to manage to run 45% of all scenarios, so installation, removal, etc. And with this optimization, we go down to 22 minutes, and we run 52 of the total of scenarios. The 48% remaining are not timeouts. They are just errors in the conversion or utilities that we have not specified. So huge improvement by just adding some laziness to our constraints. Now, that's all the tools that we had needed to write a toolchain that scales to all the packages of Debian. Let's just see quickly what a report looks like for this toolchain. That's a demo, except in the slides, so screenshots of my web browser. That's the results of the execution on runcid CGI, which is one package. We can see that it runs almost instantly, that this package has two maintainer scripts. The pre-inst has been converted successfully. The second has been rejected by conversion because it uses something that we do not know how to handle. If we scroll down, we see a summary of all the scenarios that have been run on this package. And the first one is the installation. And we can recognize, for instance, that first we do pre-inst, and then if it's okay, we unpack everything. And then if it's okay, we run the post-inst, and then we reach the state of installed. Of course, here we have no idea what happens in the post-inst because we have not been able to convert it. What we do know, however, is that if the pre-inst fails, and it can fail with in two different ways, then the post-rm tries to recover from the error, but it's not here. There is no post-rm in that package, and therefore we reach the not installed state. Not installed is not a bug per se, because it's okay for a package to say, well, I don't want to install because the machine does not look clean to me, and I don't know what to do. What is not okay, however, is to reach not installed after having performed transformations on the file system. And here, if we look at the first of the second one, labeled 1 of the not installed cases, we see a report of this form, and you can see something that looked like what we've had in this presentation, and we see that it's a case where we have a transformation from an input root, which had etc runcid lg.conf and etc runcid apache.conf. And then we have an output root, which still has the etc runcid apache.conf, but not the lg.conf anymore. So we reach not installed, but we do a transformation. We can go look at the page that gives us the original shell script, and we see that indeed it's possible that we first remove lg.conf, then we test the existence of apache.conf and we try to remove it, but the existent will answer yes if apache.conf exists and is a directory, exactly the case that is described here, but the remove will fail on a directory. And that's exactly what happens here. We fail, but apache.conf is a directory and has not been removed, and lg.conf has been removed. We have reported that to the maintainer of this package. He confirmed that this was a bug, and since then, the bug has been fixed. In the whole project, that's in total 151 bugs that we have opened found by various parts of our tool. And at the time of writing my PhD, 92 were solved, and hopefully since then more. Let me now just conclude and give you an idea of what remains to do. My thesis follows 3 angles. We have theoretical results, like the definition of this logic FTS, a work on decision procedures, and that leads to a result of decidability of the first order of a logic, and this problem was open until now. We have a dimension of modelization of real-world complex objects, the POSIX shell, and the Unix file system and utilities. This consists in reading complicated standards, working on these complicated objects, etc. And we have a dimension of implementation of really concrete things like a parser for a POSIX shell, the conversion from POSIX shell to the intermediary language, but also efficient solvers for some logic. And in the end, what we obtain is a tool chain that is able to scale to 30,000 packages. Of course, we're not done. And there is a lot of things that we can imagine doing. There is work to do on the toolchain itself. We would love to extend it to support more maintainer scripts. That would go by either extending the intermediary language to support more constructs of shell, or also write more specifications in order to get more Unix utilities in the tool, supported by the tool. One thing that I would love to do would be to add the automated testing of specifications. The idea is just that you take a utility called C, you get its specification from our tool. It's a formula of an input route and an output route. You take a file system, a concrete file system, such that it satisfies the formula, like it's a good precondition for the specification. You run concretely the utility call on this file system, which gives you an output file system. And you check that these two file systems are satisfy the specification. This can give us first a way to check that our specifications make sense by comparing them to real world, really used utilities. And then it can be the contrary. It can allow us from specification to generate a battery of tests for utilities that pretend to be POSIX compliant. And then, well, we could imagine a lot of generalizations of our toolchain to other distributions, for instance. So we've done Debian, so like Ubuntu would be easy because it's the same package manager. There would be some work, but it would be rather easy. And then we could go to other distributions that do not use the same package manager. And that would be more work, although the ideas are often the same. And then a dream, in general, it would be amazing to be able to apply this to shell scripts, to any shell script. And of course, there is a lot of work, but there is actually new work existing on the semantics of shell scripts, for instance, etc., done by Michael Kurenberg here. So there is, it would be really interesting to try to work more in this direction. That's for the tool chain. But of course, we could imagine a lot of things on the Logix FTS that we worked with. First of all, we could imagine extending it to support various things. Quantification over features, for instance. We know directly that the first order is non-decidable, but maybe we can still do things with that. Or we could handle natively path of features instead of having to chain several features together. These two together would be possibly a first step towards supporting symbolic links. And we could imagine adding predicates like a test of inclusion of trees, which would give us access to other commands that we don't know how to specify yet, like the recursive copy, for instance. So basically adding expressivity to FTS and work on that. Another funny thing to do would be to write a solver that supports the glob, and that will allow us to specify commands like remove everything that ends in foo. And we would specify this by commands, by a formula saying, well, there used to be something ending in foo, and now there is nothing ending with foo, and all the things that do not end in foo are the same. Funnily enough, my PhD already described how to do that. So that's not new theoretical research. It just consists in writing a solver and playing with it. And finally, it would be really nice to write new decision procedures, more efficient for other subsets of FTS. The first order, so here, of course, efficient is not possible, but maybe working well in practice. Or we could consider, for instance, the entailment of sigma-1 formulas. And I'll just finish by putting you back on this slide, because I think it's a great summary of both my contributions and what we've written in the tool. Thank you very much for your attention.